In this video, I'm going to walk through 3 examples of partial fraction decompositions. In each example, I'm going to take a rational expression and rewrite it as the sum or difference of 2 or more simpler rational expressions called partial fractions. Okay, just so you get an idea of what we start with and what this looks like at the end, I've written a problem up here. And we're starting with this rational expression, this 8x minus 1 over x squared plus x minus 6, and this is what you would be given. And the objective here is then to break it down into its smaller composite parts, or partial fractions is what they're called, right? So if I was to take these two and add them together, I would end up with this, okay? So more specifically for this video, I'm going to focus on rational expressions where the degree of the numerator is less than the degree of the denominator, and we call these proper fractions. So you'll notice in this case, the degree of the numerator is 1, which is less than the degree of the denominator, which is 2. Okay? Also in these 3 examples, we will be decomposing rational expressions into non-repeating linear factors. Okay, so that's important because later on I'll show you what it looks like if some of these factors repeat, or if they are higher powers instead of just linear, if perhaps they are quadratic factors as well. Okay, so let's look at this first example, and we're going to use x plus 5 for a numerator, and then my denominator is going to be x squared plus 4x plus 3. Okay, so this, first of all, we notice is a proper fraction because the degree of the numerator is less than the degree of the denominator. Also, I notice that when I factor the denominator, I have x plus 1 and x plus 3, which are linear binomials. Okay, that's really nice. So what this is going to look like here, I'm going to make a fraction for each one, x plus 1, x plus 3. Okay, so what ultimately are going to be the numerators here? And that's really what we're trying to solve for. Well, in the previous example up here that I showed you, in each case it was just a constant. So whenever we have linear factors down here, all we need is a constant. Okay, so I'm going to put a and b. And if we have more than 2 terms, obviously c, d, e, and I'll just kind of work it that way. Okay, so you're going to start out by factoring the denominator, and each of these factors gets to be its own denominator. And then since they're linear, I'm just going to put an a and a b for the constants up there. Okay, so that's how we're going to start. So what's the next step? Well, the next step is, what if I had this and I was trying to get common denominators and turn it into this? Okay. Well, I would notice that the common denominator is this x plus 1 times x plus 3. Okay, well here's the x plus 1, here's the x plus 3. Which factor is this fraction missing? Well, it's missing the x plus 3. So I'm going to take the a and multiply it by x plus 3. Okay, well which factor is this one missing? It has the x plus 3, but it's missing the x plus 1. So I'm going to put the x plus 1 with it. Okay. So of course now this is all over the common denominator of x plus 1 times x plus 3, okay, which doesn't really matter here in a second when I show you, but this ultimately equals x plus 5 over this x squared plus 4x plus 3. Okay, really right now, since these denominators are the same, I'm just going to cancel these out. I don't even care about these right now. I care more about specifically just the numerators. And so I'm going to create a nice equation out of this. A times the quantity x plus 3 plus b times the quantity x plus 1 equals x plus 5. Okay, so this is what I need it to equal. Okay, well, how do I solve this? Because it seems like I have a single equation, but don't I have 3 variables, a, b, and x? So how can I solve when I only have one equation for 3 variables? Okay, well we're going to do a fun little technique here where we're going to go one at a time and we're going to cancel out the a and then cancel out the b by putting in different values for x. Okay, well what does that look like? This first one is x plus 3 and I'm multiplying that by a. So what if I said for a second, well, let's make x negative 3. Okay? Well, if I made x negative 3, I'm going to go ahead and plug in negative 3 for all the x's. And now I have this. What do you notice that happens? Negative 3 plus 3 is 0. That cancels. So you'll notice immediately I now have a single equation with only one variable, b. So b times negative 2 equals 2. So if I divide both sides by negative 2, b equals negative 1. Hey, there's one of my values. Okay, so let's do the same thing again, but instead of canceling out the a, let's cancel out the b. So what value of x could we use to cancel out the b? Well, x plus 1, so it looks like x will have to be negative 1. Okay, so when I do that, a times, and now I'm plugging in negative 1 for all the x's, so negative 1 plus 3 plus b times negative 1 plus 1 equals negative 1 plus 5. Well, okay. This ends up being a times 2, and that goes away, and that equals 4. So when I divide both sides by 2, a equals 2. Okay? Well, now I have the constants. I'm good to go. Okay, so what does this look like now? A is 2, b is negative 1. And if we venture back up here for a second, didn't we see that a was over the x plus 1 and b was over the x plus 3? Okay, let me just write this down one more time down here. So a was over x plus 1 and b was over x plus 3. Okay, and my b value was negative 1, so I'm going to exchange this for negative 1. And my a value is 2, so I'm going to exchange that for 2. So what I really have is 2 over x plus 1, and this negative here can make this a minus, so minus 1 over x plus 3. I have now found the partial fraction decomposition for the original rational expression that we were given. Okay? So just to kind of show you, let's go ahead and rework this. Let's find the common denominators and subtract these two fractions, because I want to show you that you will end up with that original rational expression. Okay, so the common denominators will be x plus 1 and x plus 3. Okay, so this one was missing the x plus 3, and this one was missing the x plus 1. Okay, so 2x plus 6 minus x minus 1 all over this common denominator. So this ends up being 2x minus x is x, 6 minus 1 is 5, over x squared plus 4x plus 3. And hey, yes indeed, if we look at this x plus 5 and then work it all the way back up here where I was, hey, same thing, right? So I know that I have decomposed this into its partial fractions correctly. In this second example, we're going to take this rational expression and decompose it into its partial fractions. So of course, again, we'll start by factoring the denominator. Okay, and I can take a greatest common factor of x out, which leaves me with x minus 4. Okay, so starting out here, I'm going to have x in the denominator, and I'm going to have x minus 4 in the denominator. And of course, they're linear factors, so all I need to do is put constants up there, a and b. Okay, so let's rework this now as if I was, finding the common denominator and turning this into a single fraction. So I know my common denominator already is x times x minus 4. So which one is this missing? This one's missing the x minus 4. And which one is this missing? Well, it's missing the x. Okay? And of course that equals 3x minus 8 because that was the numerator I had right here. Okay, so let's kind of work some of this little math magic here. So this single equation has three variables three unknown values, and I need to find out what A and B are. So I'm going to substitute a couple of values of x to kind of suit my needs here. So it looks like I can make A go away if I substitute 4 for x. So x equals 4, so it makes A times 4 minus 4 plus B times 4 equals 3 times 4 minus 8. So I just plugged in 4 for all my x's. Looks like my a's go away, so I have 4b equals 12 minus 8, which is 4. So when I divide both sides by 4, b equals 1. Hey, that actually worked out really nicely. Okay, so what can I substitute in for x to get rid of my b? Well, it's b times x, so I guess x equals 0 would work. Okay, so let's say a times the quantity 0 minus 4 times b times 0 equals 3 times 0 minus 8. You know, zeros are really nice because that goes away and that goes away. So 0 minus 4 is negative 4a equals negative 8. So when I divide both sides by negative 4, it looks like a is positive 2. Okay, well now I know both of my values. So I'm going to rewrite this. It was a over x plus b over x minus 4. That was what I started with for my original decomposition with my constants up here. Okay, but now we know a is 2, so 2 over x, and now we know b is 1, so 1 over x minus 4. So this is my final partial fraction decomposition. But again, like I did in the previous example, let's go ahead and add these two together. I just want to show you that you're going to get what you started with, the 3x minus 8. For the numerator and then this common denominator. Okay, so let's put them together. So 2 times x minus 4 plus 1 times x all over x times x minus 4. Okay, so this is 2x minus 8 plus x over x squared minus 4x. And finally, 3x minus 8 all over x squared minus 4x. Yep, and that, if you follow me here, was exactly what we started with. So we know we've done it correctly. In this third and final example, we're going to take a little larger rational expression and decompose it into its partial fractions. Okay, so once again, we're going to start by factoring this denominator, and it looks like I have 4 terms, but it looks like it will work nicely and I can factor this by grouping. So I'm going to pull out an x squared and I'm left with 2x minus 1, and then I'm going to pull out a negative 9 and I'm left with 2x minus 1, okay, which ends up being x squared minus 9 for one of the quantities and 2x minus 1 for the other quantity. And of course I have difference of squares, so x minus 3, x plus 3, 2x minus 1. Okay, so in the previous 2 examples I only had 2 factors for the denominator, and in this case I have 3 factors for the denominator, but each one of them is linear, so we're still okay. Okay, so I'm going to set up fractions for each one of these denominators, and then 2x minus 1. And since each of these are linear, all I need is a constant, a, b, and c. Okay? So now that we have these, let's kind of rework them. So this common denominator that we have with all 3 factors, you know, which factors is this one missing? Well, this is missing the x plus 3 and the 2x minus 1. Plus b, what's this one missing? Well, the x minus 3 and the 2x minus 1. And then what's this one missing? Well, the x minus 3 and the x plus 3. Okay, so this seems pretty long here. That's okay. And again, this equals, and I'll just put it down here, this equals our numerator, which was negative 29x minus 3. Okay. So I don't have room to put it all in one line, but that's okay. We'll kind of do what we need to do anyway. So in order to get rid of these one at a time, let's use the different values of x. So if x equaled, we'll start with this one. If x equaled positive 3, okay, then I would end up with a times 3 plus 3 is 6, and then 2x minus 1. So 2 times 3 is 6, minus 1 is 5. Okay, so 30a. And the next one would end up being 3 minus 3 is 0. Okay, so that would go away. And the next one would be 3, so that one would go away. So I have now negative 29 times 3 minus 3. Okay, well, what's that going to end up being? Looks like negative 90, because this is negative 87 minus another 3. Hey, that actually works out not too bad. So it looks like, what, negative 3. Okay? So let's go ahead and get rid of the next one. So x plus 3. So let's use negative 3 for x. Okay? So when I do negative 3, the first one goes away. The a goes away. But I still have the b. And it's going to be b times, okay, so negative 3 is my x. So follow me here. So if negative 3 is my x, it's going to be negative 3 minus 3 is negative 6. And then 2 times negative 3, which is negative 6 minus 1, is negative 7, okay, which would be 42b ultimately. And then when I do negative 3 here, the c will also cancel. Okay, so the negative 3 that I plugged in, we'll do this. So negative 29 times negative 3 is positive 87 minus 3 is 84. Hey, that actually was pretty nice too. So it looks like b equals 2. Okay, so finally then, the last one is 2x minus 1. So if I put a 1/2 in here, 2 times a half is 1, 1 minus 1 is 0. So I'm going to say x equals 1/2. Okay, so let's work the whole thing now. So when I plug 1/2 in here, the a's cancel because of that 0. When I plug 1/2 here, the b cancels, so because that's 0. So the only other one I have is c times, okay, 1/2 minus 3 and 1/2 plus 3. Okay, so I'll kind of show my work here. So it's 1/2 minus 3 and 1/2 plus 3, and that's going to equal negative 29 times a half minus 3. Okay, so I got some fraction business here to do. Okay, so 1/2 minus 3 is going to be negative 5/2. 1/2 plus 3 will be 7/2. And this will be negative 29/2 minus 3, or minus 6/2. I can just get common denominators there. So this ends up being negative 35/4 c equals negative 35/2. Okay, so solving for c, so let's multiply both sides by the reciprocal. So negative 4 over 35, negative 4 over 35. So c equals, okay, the 35's cancel, the negatives cancel, the 4 and the 2 cancel and make it 2. Whew, that was an awful lot of work just to get 2. Okay. So my a, let's go ahead and write these down here. My a was negative 3, my b was 2, and my c was 2. And originally I had a over x minus 3 plus b over x plus 3 plus c over 2x minus 1. And since now I know all those values, I know that my fraction, negative 29x minus 3 all over this 2x cubed minus x squared minus 18x plus 9 equals, okay, so here was our original little rascal, and its fraction, partial fraction decomposition is negative 3 over x minus 3 plus 2 over x plus 3 plus 2 over 2x minus 1. Okay, right there is what I have incomplete for the answer for the third and final example for this video.